Today's problem is to search in fully rotated, sorted 2D matrix. Difficulty is medium. Accuracy is very high, 69.25%. This is, difficulty medium. This seems like a hard problem to me. The accuracy is unbelievable. 20-minute average time. I mean, even if you know how to do this, kind of, it seems like a hard problem. So maybe it's a medium problem because there are a couple of, similar problems that are pretty well known, and you can use those to solve this problem. Well, enough about that. Let's look at what the problem is. You are given a 2D matrix of size n by m that was initially filled in the following manner. Every row is sorted in increasing order from left to right. First element of every row is greater than the last element of the previous row. Okay, so really it's a sorted array, just, split up into rows to make a matrix, but it's a sorted array, start to finish. This implies that if the matrix is flattened row-wise, it forms a strictly sorted 1D array. Later, this sorted 1D array was rotated at some unknown pivot. The rotated array was then written back into the matrix row-wise to form the current matrix. Given such a matrix and an integer x, determine whether x exists in the matrix. Okay. There's a pretty well-known problem as far as like finding a target in a sorted matrix. All right, let's forget the rotation for a minute and just imagine that we have one of these, strictly sorted 1D arrays split up into rows. Okay, well, you can do a binary search on that. It's just the only challenge is to, your high, your low pointer is going to be 0. Your high pointer is going to be m times n, and then add them together, divide by 2, and there's your mid. But now you have to convert mid into 2 indices, and you can do that by doing a div by n. Is that not n, m, the length of the row. Div by m mod m. Okay, and then that gives you that's your mid. And from that point, it's just a regular binary search. Okay, now there's another problem where you search in a rotated, sorted array. Okay. How do you do that? You can use binary search for that too. But now that has been converted into a matrix problem. So now instead of a rotated sorted array, you've got a rotated sorted matrix, right? Well, again, you can do the same thing. You can do a binary search. Now you're going to need to convert all of your pointers, high, low, and mid, to 2D, to 2D coordinates. Okay, so, you kind of know how to do it, but still, there's a lot of ways to go wrong. Let's look at some of the problems here. Now, one thing that we can rely on here is just like the 1D array problem, you rotate it, and half of the array at least well, at least one half of the array is going to be sorted. Okay. This one, for example, we've got a rotated sorted matrix, but you can see that 7 through 13, that is, how many things in there? Yeah, that's more than half of the array. That's still sorted. Okay, so we use that as part of our solution. Same thing with this one. We have 9 elements. 5 of them are still sorted. That would be the 1, 2, 3, 4, 5, and then we'll go through how to apply a binary search to it. N times m is going to be between 1 and 10 to the 5th. The elements of the matrix, as well as the target, will be between 1 and 10 to the 6th. Expected complexities, log of n times m. Yeah, because we're doing a binary search and the topic tags binary search. Okay. Auxiliary space O of 1. I think, oh, let me think about this for a second. O of 1, are we counting the stack space? Hang on a second. All right, as I think about this, I may have cheated a little bit. Not cheated, but I did write the recursive search. I mean the binary search recursively. Now you could write the binary search iteratively, and you wouldn't be using any extra stack space. But now that I noticed that O of 1 auxiliary space, I don't really feel like rewriting the whole thing. Okay. Now let's go through this. We have n and m. I put them up here at the top so that we can use them without passing them the binary search. We're already passing 4 parameters to it. And I guess we could, recompute them every time, but that doesn't seem that fruitful either. All right, here's the search matrix. We have a matrix and we have a target. N is the length of the matrix. M is the width of the matrix. Low starts out as 0. High starts out as M times N minus 1. And we call the binary search with the matrix, with the low pointer, the high pointer, and the target, X. All right, binary search. Well, if the low pointer crosses over the high pointer at some point, we didn't find X, so we just return false. Next, we calculate the mid pointer. We convert the mid pointer to row and column. We do that with a div m mod m, m being the width of the matrix, and we get the value at that row and column. Does that equal X? If it does, we're done. We just return true. But if it doesn't, then we do the same thing with the low pointer. That is, we convert it to row and column, div m mod m, and get the value at low val. Now, as I said, half the matrix at least is sorted. We don't know which half yet, but let's find out. Now, if the low val is less than or equal to the mid val, then the left half is sorted. Okay? Now, then we have to make one more decision, and that is if it's sorted, we can see is X between low val and mid val, and if it is, then that's that's the half that we want to keep. We want to keep the left half. and recursively binary search it. So we would make another call a binary search with the matrix with the low pointer where it is, the high pointer moved down to mid -1 and the target. Otherwise, it's in the right half. So we'll do the recursive binary search with matrix with low moved up to mid +1, high, and the target. Now, if the left half is not sorted, then the right half is sorted. So we're going to calculate row and column for the high pointer. Again, div m mod m. We're going to check what the high value is, looking in the matrix at that row and column. Now, if the mid-val, if x is between the mid-val and the high-val, then that's where, that's the half that we want to binary search. It's in the right half. So we will binary search matrix, will move the low pointer up to mid +1, keep high where it is, and x. If it's not there, that means it's in the left half. So we'll do the binary search with the matrix, low pointer where it is, move the high down to mid -1 and the target. All right. That's it, and we'll continue to do that until we either are able to return true because we found it or because the pointer's crossed over and it isn't there. All right, let's do a quick sanity check on this. What did we get? All right, well, that one case worked. All right, let's run it. I hope there's not an issue with the recursive binary search. No, okay. All right, good. That's it. So, yeah, I mean, I encourage you, I always encourage you, of course, to try the problem before looking at the solution. But I also encourage you, if anything is confusing here, you can walk through this. I didn't walk through it because it would take a long time. You can also look for either on Geeks for Geeks or LeetCode. One or both will have it. The two related problems, which is searching in a sorted 2D matrix, and the other is searching in a rotated, sorted, a rotated, sorted array. All right, so please like the video. Go ahead and subscribe to the channel. It's free. I'll send you problems of the day in your inbox every weekday. And we'll see you next time.